Welcome to Related Rates Example 3 by Conceptual Calculus. In this video, we use the procedure introduced in an earlier video to solve a new related rates problem. A small boat is tied to a dock. The water level drops, causing the boat to move lower and closer to the dock. The water level is dropping at a rate of 3 inches per hour. How rapidly is the boat moving toward the dock at the moment shown, when the boat is 5 feet below and 12 feet east of the dock? We are not told how long the rope is, but we can find it. The rope forms the hypotenuse of a right triangle, so we can use the Pythagorean theorem. The square of the length of the rope is 12 feet squared plus 5 feet squared. From that, we find that the rope is 13 feet long. We have information about where the boat is and how fast it is moving. The basic quantities are the position information. The rate of change of position is the speed information. Our variables should represent the basic quantities, the position. At the moment shown, the vertical distance from one end of the rope to the other is 5 feet. But it does not stay 5 feet. As the water level drops, the vertical distance gets longer. That makes it a variable. I am going to call the vertical distance y. As the water level drops, the boat is pulled closer to the dock, so the horizontal distance is also changing. I'm going to call it x. Notice that the diagonal length of the rope is a constant 13 feet, so it does not get a variable name. Variables are things that change. The length of the rope does not change. Next, I need an equation describing how x and y are related. They are at right angles to one another, so we have a right triangle. This means we can use the Pythagorean theorem. X squared plus y squared equals the square of the length of the rope. I'm going to move that equation to the top of the page and multiply out 13 squared to get 169. Next, we differentiate both sides of the equation with respect to time. This requires implicit differentiation, which is an application of the chain rule. We treat x and y as functions of t. When we differentiate x squared, we get 2x. But then, we have to multiply that 2x by the derivative of the quantity inside that square. That gives us 2x dx dt. The derivative of y squared works the same way. We get 2y multiplied by the derivative of the quantity inside the square. The variable inside the square is y, so we need dy dt. On the other side of the equal sign, we need the derivative of 169. The derivative is the rate of change. Constants do not change, so their rate of change is 0. Next, we solve for the thing we were asked to find. The question asked, how rapidly is the boat moving horizontally toward the dock? The horizontal distance is x, so to find how fast that is changing, we want dx dt. If we divide both sides of this equation by 2x, we can get dx dt alone on one side of the equation. Now, we substitute the given values into this equation to get a value for dx dt. At the moment of interest, y is 5 feet and x is 12 feet. The units of feet will cancel, leaving that fraction as simply 5 over 12. The only remaining units are the units of dy dt, so we can use any convenient units there. I'm going to stick with the given 3 inches per hour, although you could convert to feet per hour if you wanted to. Note that the boat is moving downward, which increases the distance y, so dy dt is a positive 3 inches per hour. This gives us dx dt equals negative 1.25 inches per hour. Next, we check whether that result makes sense. The boat is getting closer to the dock, so x is getting smaller. That means dx dt should be negative. We found a negative result, so that's encouraging. What we found is the instantaneous speed of the boat at the moment when y is 5 feet. That is not the same as the average speed over a period of an hour, but it's likely to be close. Let's find out how far the boat moved in an hour, starting when y was 5 feet. At the end of an hour, y has increased by 3 inches, which is 1/4 of a foot, so the new value of y is 5.25 feet. Using the Pythagorean theorem, we find that x is 11.893 feet, which means x has changed by 0.107 feet. Converting that to inches, we find that the horizontal position of the boat has changed by 1.29 inches over the hour. This gives the average speed over an hour as 1.29 inches per hour. We don't expect the average speed to be exactly the same as the instantaneous speed of 1.25 inches per hour, but it is close, which suggests that our result is probably correct. The last step is to state the result in terms of the question with units. If the question had been, what is the value of dx dt, then dx dt equals negative 1.25 inches per hour would be a fine answer. But it wasn't. The question was, how rapidly is the boat moving horizontally toward the dock? So, that is the question we answer. We write, the boat is moving horizontally toward the dock at a speed of 1.25 inches per hour. Now we are finished. For another example using related rates, see our next video. Thank you for watching Related Rates Example 3 by Conceptual Calculus.